Good morning to all of you. Welcome to my YouTube channel. This is my first chapter for class 11, set theory. In set theory, first concept is definition of set. So a set is nothing but it is a well-defined collection of objects. Now, what is meant by well-defined in mathematics? A set is said to be well-defined if there is no ambiguity as to whether or not an object belongs to it. That is, a set is defined so that we can always tell what is and what is not a member of the set. Set theory deals with the operations between, relations among, and statement about sets. Now, basic notation for sets. Uh, all these sets can be represented by capital letters, capital alphabets A, B, C, and so on. We can denote a set S in writing by listing all of its elements in curly bracket. So to represent any set, there are two methods. One is listing method and the other is set builder form. In listing method, we just write the elements or members in this curly bracket, and in set builder form, for any preposition px over any universe of disclosure such that the set containing x where px is the set of all x such that px can be written like this. One example is given here, x where x is an integer where x is greater than 0 and x is less than 5, like that. Basic properties of sets. Sets are inherently unordered, means the order is not necessary for that. Suppose this is the set containing ABC, so we can write this one as A, C, B or BAC, like that. The order can be changed. All elements are distinct or unequal. Multiple listings make no difference in it. Like this ABC can be written like this, but this is same as this one. So this set contains at most 3 elements only. Definition of set equality. Two sets are declared to be equal if and only if they contain exactly the same elements. In particular, it does not matter how the set is defined or denoted. For example, one set is given, set containing 1, 2, 3, 4. This is same as x, set containing x where x is an integer, x greater than 0 and x less than 5. The example was taken before also. So these sets are equal. We can also write like this, x where x is a positive integer whose square is greater than 0 and less than 25. Infinite sets. Conceptually, sets may be infinite, that is not finite, without an, or unending, uncountable. Symbols for some special infinite sets are, first is natural number, set of natural numbers. We know that this was there in our lower classes, primary classes, secondary classes. We have learned natural number. The number which starts from 1, 2, 3 and it goes on is called natural number. Then integers. Set of integers contains all the natural number with their negatives, along with their negatives and 0. So 0 and the natural number set along with their negatives forms the set of integers. R, capital R, is the set of real numbers. Some infinite sets are there which cannot be put in this listing form. So R is also a set of real number is also an infinite set. Infinite sets come in different sizes. Venn diagram. Now, what is Venn diagram? The graphical representation of sets is known as Venn diagram. Sets can be described with the help of diagrams. So one mathematician, John Venn, was there. He had introduced this diagram, so it's known as Venn diagram. See, in this diagram, you can see that integers from -1 to 10 are given. Okay, -1 to 10 are given. Then this set contains integers from positive integers from 1 to 9. Then this set contains odd numbers from 1 to 9. This is even numbers from 1 to 9. And this circle contains the prime numbers from 1 to 9. Okay. So integers from 1 to 9, then Positive integer less than 9, less than 10 actually. Even integers from 2 to 9, this set. Odd integers from 1 to 9 as I see it. This is prime numbers less than 10. So basic set relations member of. Now see this thing. This is the epsilon. Greek letter is there, epsilon. Meaning of this is in or belongs to, is a member of, is an element of, like that. X belongs to S, we'll read it as X belongs to S, X is in S, is the preposition that objects X as an element or member of the set. For example, 3 belongs to N, A belongs to X, where X is the letter of the alphabet. Can define set equality in terms of this belongs to relation also. This symbol, remember this symbol for all, this is called for all. S and T, for all set S and T, S is said to be equal to T whenever for all X belongs to S, we have X belongs to T, corresponds to. Whenever X belongs to S, X belongs to T. So two sets are equal if and only if they have all the same members. Now this is X does not belongs to S. That is X is not in S or X is not a member of S. The empty set, the null set, the set which contains no element. This is the symbol of empty set. It's phi, phi, null set, empty set. It is the unique set that contains no elements whatsoever. So phi can be written like this. Null set can also be written by these two ways. One is phi and the other is curly bracket with no members in it. Two examples are given here. One example is X, where X is a leap year between 1904 and 1908. 1904 and 1908 के बीच में leap year. X, where X is a multiple of 5 between 6 and 9. So nothing will come like that. Subset and superset. Now see, this is the sign of subset and this equality sign is there. Okay. So if only this sign is there, then this will be called proper set. In next slide we'll see. S is a subset of T, means that every element of S is also an element of T. When will you say that one set is a subset of other? When all the elements of one set is in other. So S is said to be subset of T when all the elements of S will be in T. So as subset T, double implies. Double imply means if this is possible, then this will be possible. This is possible, then this will be possible. So as subset T, double implies for all X belongs to S, we have X belongs to T. One thing should be remembered that null set is the subset of every set, each set, and each set is subset of itself. So every set, actually two subsets of every set can be known, they are known to us. Two subsets of each sets are known to us. One is phi, that is null set, and the other is set itself. Now this sign, this is the sign of superset. S is a superset of T, or we can say that T is a subset of S. If S is a subset of T, then T is a superset of S, like this. So S is a superset of T here, means T is a subset of S. Note that S is equal to T whenever S is subset of T, and this is the sign of and S contains T. S is not a subset of T means that there exists X where X belongs to S and X does not belongs to T. Now proper subsets and superset. Now this sign, this is used for proper subset and this is not proper subset. Okay, in this one we include null set and the set itself. In this one, null set and set itself is not included. So S is a proper subset of T means that S is a subset of T, but T is not a subset of S. That is, S is not equal to T. Similar for S contain T also. We can see one example by Venn diagram. 1, 2. Set containing 1, 2 is a subset of set containing 1, 2, 3. Because all the elements of this set is in this one, and this is having 3, one more element 3 in it. Sets are objects too. The objects that are element of a set may themselves be sets. Let us understand this by example. Let us take one set S where X is a set containing X, where X is a subset of 1, 2, 3. Means this X is itself a set. This may be null set, this may be set containing 1, this may be set containing 2, set containing 3, like this. Set containing 1, 2, set containing 1, 3, and all this. Now remember this. Note that 1 is not equal to set containing 1. This set, in fact, this one is called singleton set. The set which contains only one element in it is called singleton set. Okay. Now this one, this sign is read as cardinality of S. Sometimes it is denoted by N of S. Ns is a measure of how many different elements S has. Cardinal number of phi is 0. Cardinal number of this 1, 2, 3 is 3. Cardinal number of AB is 2. And cardinal number of this one is, what is the answer? It's 2. It is 2. We say S is infinite if it is not finite. What are some infinite sets we have seen already? N, Z, and R. The power set operation. The power set PS of a set S is the set of all subsets of S. PS is equal to set containing X, where X is a subset of S. In power set of AB, which elements will be there? Or power set of AB will contain, it will contain phi, null set, set containing A, set containing B, and set containing AB itself. So this is the example of power set of AB. Note that for finite set S, we have number of elements in PS, or it can be written like modular sign, no, absolute value sign, but this is cardinal number of PS. Formula is 2 raised to n, where n is the number of elements in the set S. Ordered tuples, ordered n-tuples. For n belongs to capital N, an ordered n-tuples or a sequence of length n is written like this pairs. The first element is A1, then A2, and so on, etc. These are like sets, except that duplicates matter and the order makes a difference. In coordinate geometry also you learned that 1, 2 is not equal to 2, 1, because 1 here is x coordinate and 2 is y coordinate. In this one, 2 is the x coordinate and this is the y coordinate. In extra, we learned this one. Empty sequence, singlets, pairs, triplets, quadruples, quintuples, and this is n-tuples. The formula of n-tuples, the representation of n-tuples is this one. Cartesian product of sets. Cartesian product is there in chapter number 2, but we must know about this in set theory. So let us define the Cartesian product of two sets. For sets A and B, their Cartesian product is denoted by this cross sign. We'll say that A cross B, or Cartesian product of A and B, is equal to the set containing ordered pair AB, where A belongs to capital A and small b belongs to capital B. This means and. For example, we want to find the Cartesian product, cross product of these two, set containing AB and set containing 1, 2. What will we do? We'll take this one as fixed, then A1, A2, like this B1, B2. Okay. Note that for finite A and B, NA cross B is equal to NA into NB. The cardinal number of A cross B will be NA into NB. Cardinal number of A into cardinal number of B. Note that the Cartesian product is not commutative. A cross B is not equal to B cross A. We can extend this Cartesian product for more than 2 sets also. It can be extended till n number of sets. A1 cross A2 and it so goes on cross AN. Now the union operators, some operations in set theory. First one is union operator. For sets A, B, their union A union B is the set containing all the elements that are either in A or. This is the symbol of or in logical reasoning mathematics. This is the symbol for or, and we have already seen the symbol of and. This is the symbol of and. Okay. So for sets A, B, their union A union B is the set containing all the elements that are either in A or in B, or of course in both. So in A union B, you have to take all the elements of A as well as all the elements of B, but the common element should be taken one time only. Formally, for all sets A and B, A union B will be written like this: set containing X where X belongs to A or X belongs to B. Note that A union B contains all the elements of A and B. It contains all the elements of B. For all A and B, A union B is A union B contains A, or we can say that A is a subset of A union B. Similarly, B is the subset of A union B. A union B contains B, or we can say that A union B is a superset of A. Here A union B is a superset of B. So A union B is a superset of A and A union B is a superset of B. Union examples are given. These are the two sets their union have taken. These two sets their union have taken. Okay. This is the required form. Like this we can take. The intersection operator for sets A, B, their intersection. A intersection B is a set containing all the elements that are simultaneously in A and in B. Formally, for all A, B, A intersection B is equal to set containing X where X belongs to A and X belongs to B. Note that A intersection B is a subset of A and it is a subset of B. In previous union operator, we have seen that each set is a subset of the union. In this one, intersection of two sets is the subset of the two sets. That is, A intersection B is a subset of A and A intersection B is a subset of B. So remember this. Intersection examples. Now see these two sets. Same examples I've taken and common between them is nothing. In this one, common is a singleton set containing 4. So this is how we can find intersection. Disjointedness. Two sets A, B are called disjoint, that is unjoined, if and only if their intersection is empty. A intersection B is equal to 5. Example is given: the set of even integers is disjoint with the set of odd integers. Inclusion-Exclusion Principle. Now this is the most important formula which is going to be used in the statement problem based on set theory. Okay, how many elements are in A union B? So the formula is NA union B is equal to NA plus NB minus NA intersection B. See this one, the number of elements in this one we can find. Subtract out the items in intersection to compensate for the double counting them. Okay, NA union B is equal to NA plus NB minus NA intersection B. Set difference. For sets A, B, the difference of A and B written as A minus B is the set of all elements that are in A but not in B. A minus B, that is difference of set A and B, is equal to set containing X where X belongs to A and X does not belongs to B. It is also called complement of this B with respect to A. Set difference example is given here. If we want to find difference of this set 1, 2, 3, 4, 5, 6 minus 2, 3, 5, 7, 9. So we'll subtract this 2, then 3, then 5, then 1 remain here, 4 remain here, 6 remain here. So answer is 146. Similarly, z minus s, n, z integer, set of integers minus set of natural number will give us set difference by Venn diagram. A minus B is what's left after B takes a bite out of A. The universe of discourse can itself be considered a set. Call it a U. U is the universal set. The complement of A written by A bar or A dash is the complement of A with respect to U. That is, it is U minus A. For example, if U is equal to N, then if we want to find the complement of set containing 3, 5, then it will be 1, 2, 4, 6, 7, and so on. More on set complements. An equivalent definition when U is clear, A bar or complement of A is equal to set containing X where X does not belongs to A. Now see, this one is universal set, this is set A. So if this is subtracted, A bar will be formed complement of A. Okay. Some identities of set are given. First identity, A union phi is equal to A and A intersection U equal to A. So domination property, A union U is equal to U and A intersection phi equal to phi. Idempotent law, A union A is equal to A and A intersection A is also A. Double complement, A double dash or A double bar is equal to A. Commutative property for union and intersection, A union B is equal to B union A and A intersection B is same as B intersection A. Associative law, A union B union C will be same as A union B union C. A intersection B intersection C will be same as A intersection B intersection C. Now distributive law, A intersection B union C will be same as A intersection B union A intersection C. We'll take intersection of these two and then union will come and intersection of these two. So A intersection B union C is equal to A intersection B union A intersection C. We'll say that intersection is distributive over union. Now these are the most important laws in the complementary set theory. DeMorgan's law, exactly analogous to and derivable from DeMorgan's law for proposition. A union B the whole dash is equal to A dash intersection B dash, or A intersection B complement is equal to A complement union B complement. How will we learn this? How? It will be easy to learn if you will read like this. Complement of the union is equal to intersection of the complement, and complement of the intersection is equal to union of the complement. Okay, this is the easiest way to learn this. Now proof of De Morgan's law by Venn diagram, it is given. This one is A union B, so this will be A union B the whole dash, and this will be equal to A dash intersection B dash. De Morgan's laws proof by the way of definition. We want to prove that complement of the union equal to what? Intersection of the complement. So in this one, if we want to prove that two sets are equal, then we'll show that A is a subset of B and B is a subset of A. Then and only then A is equal to B. Here we want to prove that complement of the union is equal to intersection of the complement. So we'll take this one as we'll prove that this is subset of this one and this is subset of this one. So first part, say X belongs to this part, complement of the union. X belongs to A union B, the whole bar or the whole dash or the complement of A union B. This means that if some element belongs to complement, then it does not belongs to that set. So X does not belongs to A union B. This means that if X is not in the union, then it must not be, it will not be there in both the set. X does not belongs to A as well as X does not belongs to B. So we'll write X does not belongs to A and X does not belongs to B. Now X does not belongs to A means X belongs to A bar, that is complement of A. Similarly, X does not belongs to B means X belongs to B bar or B complement. Now X belongs to A complement and X belongs to B complement. So we'll write X belongs to A complement intersection. This and will give us intersection sign. X belongs to A complement intersection B complement. So we have started from this and we have proved this one. This means that A union B complement is a subset of A dash intersection B dash, A complement intersection B complement. Now let us take some element in this and we will show that that element belongs to this. So X belongs to A bar intersection B bar, or X belongs to A complement intersection B complement. So X does not belongs to A because X belongs to both this. So X does not belongs to A and X does not belongs to B. Now X does not belongs to A and X does not belongs to B. That means it must not be in the union also. If it is not in the union, then it will belongs to the complement of the union. Hence we have proved this one, the first identity. The second identity you can prove by this method. This is very easy. You try it yourself, friends. Proving set identities. To prove statements about sets of the form E1 equal to E2, where E's are the set expressions, here are three useful techniques. Prove E1 subset of E2 and E2 subset of E1. This we have already used in the previous one. Use logical equivalence and use a membership table. Okay, but we in NCERT CBSE we are using this one. Okay. One example is given: mutual subsets show that A intersection B union C is equal to A intersection B union A intersection C. In fact, this is the distributive property. Okay, so we'll prove that this is the subset of this one, then this will be the subset of this one, then it is true. We are through. So assume X belongs to A intersection B union C, and we want to show that X belongs to this. We know that X belongs to A and either X belongs to B or X belongs to C. So case 1, X belongs to B. X belongs to A is there and X belongs to B. That means X belongs to A intersection B. So X belongs to A intersection B union A intersection C. Now next case, suppose X belongs to C. So X belongs to C, that means X will belongs to A intersection C. Now X belongs to A intersection C, so in this case also X will belongs to A intersection B union A intersection C. So we have started from this one, X belongs to A intersection B union C, and we have showed here that X belongs to A intersection B union A intersection C. That means this is subset of this one. Similarly, we can prove the second part. Okay, and if these two sets are subset of each other, that means they are equal. This is actually distributive property. Okay, that intersection is distributive over union. Generalized union. Binary operation. Binary union operator A union B is there. Binary means there are two sets. And array unions, suppose there are n sets, A1 union A2 union and so on union AN. So this can be written like this. Grouping and order is irrelevant. So big U notation. This is the symbol for union of all this I running from 1 to n AI. Union AI where I is running from 1 to n. This is the way to read it. Or for finite sets of sets, we'll say union A where A belongs to X. This is generalized union form. Generalized intersection form, same as union we did. So this is big arch and this is the intersection. I is running from 1 to n AI. So this is the end of the lesson, friends. Concept was about set theory. Thank you all for watching this video. If you have any doubt, you can ask me, you can comment. Thank you.